Okay. So good morning, everybody. My name is Sandro Scandolo. I'm going to give you a course on solid-state physics. So let me start by writing my name here. And as you certainly know, this is going to be a course on solid-state physics. I guess some of you already know me, or you've seen me around, right? I'm a member of the condensed matter group here at the ICTP. By the way, if you want to reach me, my email is, and I'll write it here, just my last name. Okay, and also my room number is 248 here in the Leonardo building. Although if you want to see me, I strongly advise you to write me an email before so that we can set up an appointment. I don't have any regular time for meeting students, but just write me an email if you want to talk to me, and I will reply, and I will arrange an appointment. Okay, so let me begin by defining what we're going to talk about. By the way, how many of you have already taken a course in solid-state physics? Can you raise your hand if you've already taken a course in solid-state physics in the past? All of you? Great. Okay, so I don't need to give this course, perhaps. Well, anyway, I mean, we are now going to do it in a probably different way with respect to what you have seen in the past. I'll try to make connections with quantum mechanics. And I try to, also my course is typically a little bit more on the material science side of solid-state physics. So I try to explain how materials work, what are the properties of materials, and how we understand the properties of materials based on the basic laws of quantum mechanics and classical mechanics. So I will be, perhaps with respect to past courses that you have taken in solid-state physics, my course is going to be a little bit more on the material science side, on the applied side. Just because I think, I mean, that's my own personal perspective on physics, that physics must be useful, right? Nothing, I mean, against particle physics, of course. Particle physics is useful for other reasons, but I have my own opinion that if I do physics, I want to try at least and give a contribution to society, and the quicker way to give a contribution to society is by trying to study physics, which has some implications for society. Of course, my colleagues in particle physics would immediately contradict me and tell me that the World Wide Web wouldn't exist if the accelerators, right, the CERN in Geneva didn't exist. You're probably all familiar with the fact that internet was invented in Geneva, where they were building the big accelerator. So, I mean, of course, the consequences of what we do in physics to society are difficult to predict. Okay? But there are probably more chances that you can do something useful if you study solid-state physics than if you study particle physics. It's just the end of the advertising for solid-state physics. Okay, so what do we mean by solid-state physics? We mean the study of materials, of objects, objects we're all familiar with, but trying to understand the properties at the microscopic level. By microscopic level, of course, I mean the atomistic level. So we're going to try and understand the properties of materials, starting from the understanding of these materials at the atomic level. We want to understand why, for example, a material is hard, but we want to understand it based on the properties of how the atoms bond to one another. Or we want to perhaps understand why a material is conductive, and we want to understand it based on the properties of the electrons that are in this material. So let me begin this trip in solid-state physics by trying to, I mean, at least identifying out of the objects that we see around us, how we can understand the properties of these materials. And we'll, of course, examine this in more depth in the future. But at least let's take some materials that we're all familiar with, right? I mean, this piece of plastics, for example, that's not wood, by the way. This is probably plastics, okay, the table here. Do you know what plastics is at the microscopic level? If you had a microscope, you were trying to look with a microscope at the atomic level, what would you see? chain of molecules, I mean long chains of molecules. So let's begin this discussion by just taking a microscope and look at what this plastic is made of. This plastic, if you had a powerful enough microscope, you would see chains. You would see chains of atoms typically made of carbon, like this. Very long chains, by the way. And attached to carbon, you would find some hydrogens in different proportions. But if we want to deal with a saturated hydrocarbon, I'm not implying that you need to know all this. I'm just discussing, very general terms, right? Things that you might be already familiar with. By the way, when I talk about these things, I'm clearly talking about chemistry, not about physics. But there is a lot of interplay between solid-state physics and chemistry. So you will realize that the concepts you have learned in physics are as useful as the concepts you have learned in the past in chemistry when you understand solid-state physics. So here, this is clearly a chemistry drawing. You have carbon atoms, you have hydrogen atoms. This is a long chain. In this particular case, we are talking about polyethylene. It's a particular polymer. It's a very popular one, by the way. It's probably the most common polymer we know. It's very common because it's very simple. It's just made of carbon and hydrogen. And you might have realized, if you remember your chemistry background, that carbon is fourfold coordinated. So something must click in your mind, probably, right? This is a very stable configuration for a carbon atom, sp3 hybridization. We'll come back to this, but I just wanted to refresh some concepts that some of you might already be familiar with. Okay, so we have sp3 hybridization. Carbon is very happy, and it's fourfold coordinated. It forms this chain. Hydrogen is also happy because hydrogen is only one electron, so it forms one bond. So we have a very stable chain, and this is called polyethylene. Or PE. This is one of the most common polymers that we find on. This is presumably made of polyethylene. Plastic bags are made of polyethylene, for example, right? Anything that you see here which is made of plastics is likely made of something similar to this, with some chemical changes. You may mix up a little bit of oxygen, nitrogen, fluorine. If you take Teflon, Teflon is the plastics that covers your pans, right? The frying pans. Teflon is essentially polyethylene with the fluorine substitutions instead of hydrogen. So this is a very common motif in polymer physics and in plastics. Of course, there are huge, thousands, millions of different chemical varieties of polymers that you can construct with different properties, of course. Now, one of the peculiar properties of polymers is that they're long chains. And so when they pack, unfortunately, they pack in a very disordered manner. If you try to take long strings and try to put them together, they will, of course, all messed up. And this is the same. So if you look at the structure of this plastic material, for example, like any other plastic that you see around, you'll see that these chains are packed in a very disordered way. Okay, so this would be the polymer, and this would be a very disordered way of packing these linear chains. By the way, what distinguishes, for example, plastic bags from the cover of a table is the way these chains pack. Plastic bag is very soft, right? This cover is very hard. Turns out that if this packing is very tight, the mechanical properties of plastics that are a consequence of this tight packing is hardness. If the packing is loose, that is, if there is a lot of empty space, then of course the material is much softer. And so you have plastic bags. In fact, you typically distinguish polyethylene to low-density and high-density polyethylene. This is high-density polyethylene. Plastic bags are low-density polyethylene because there's plenty of space in between. So this is a very nice example, I guess, of how understanding the microscopic properties of a material allows you to understand the macroscopic properties of a material, right? I guess it might not be obvious for the person in the street that this material here is the same as the one that makes plastic bags. It is the same from a chemical point of view, from an atomistic point of view. They differ, however, in the way the chains pack in forming the solid. Of course, then the question is, how can I produce out of this chain a material which is packed in the way I want, right? And then there are all these engineering techniques that allow you from the melt or from different chemical processing to obtain a material with a different density and therefore with different mechanical properties. But this is not, of course, solid-state physics. We're really entering into the realm of engineering more than physics and chemistry, or how we should say. Yes?
I have a question, but I don't know whether it's important or not. Can we have like a continuous conformation? Okay, I mean, here now we differentiate the plastic with like this one with the conformation, right? Mm-hmm. And then can we have like a continuous conformation?
You mean an infinite chain, or what do you mean any continuous, or different?
We have, okay, the basic units of the chain is the same, mm-hmm. But since the conformation or the packing is different, we have plastic and we have something.
Right, right.
But okay, can we have something in between? I mean, like it is a continuous property.
Oh, so your question is whether we can have a macroscopic change of the density, for example, of the plastics in such a way that it's soft on one side and hard on the other side. Is this what you mean?
Yeah.
Or at some sort of mesoscale, intermediate between microscopic. Of course, it is possible. I'm not myself familiar with this, but it is entirely possible that by growing the polymer, by appropriately choosing the way you grow the polymer, you might be able to create a polymer with different mechanical properties at the mesoscale, so at a scale which is neither the microscopic one nor the big macroscopic one. We are familiar, yes. Yes, that's entirely possible, yes. I'm using polymers not because we're going to study polymers too much during the course, but just because I think it's a nice example where you see the different ingredients, the chemistry, the mechanical properties, and then the macroscopic world as a clear example of how this reflects the microscopic, the atomistic properties. But there are plenty of other examples, right? There are actually, let's take any other material. Now, it's difficult now to find something which is not plastics around us. You want to discuss the board, the blackboard? This one? This one? What do you mean? The frame. Yes, that's a very good example. What is this frame made of? Do you know? Good. This is aluminum, right? It's aluminum if you're British, or aluminum if you're American, okay? So this is clearly a piece of aluminum, right? You see it from the slightly shiny appearance. So it's a piece of metal, okay? And I guess you're all familiar with the fact that metals are certainly not polymers. They're completely different. So what would I see if I took a microscope and I would try to see what is this piece of metal? I would see aluminum atoms, right? Aluminum is an element. So presumably, this object here is made of entirely of a single element. Or, say 99.9% made of a single element with some impurities, of course. But let's forget about the impurities now. Let's focus on the bulk. So this is a piece of aluminum. So if I had my microscope, with the same microscope I used to take a look at this polymer, at plastics, let me try and magnify a little piece of aluminum here. So what would I see? I would see atoms, right? I would see aluminum atoms. But I would see them packing in a much more ordered way. No, don't ask me to fill up this thing. I would see atoms packing in a very regular way. This is, of course, because aluminum, unlike carbon or hydrogen, is an atom that likes to have many neighbors. This is not something we're going to discuss in too much detail, of course, because this is really chemistry. But I guess, you might be already familiar with the fact that there are elements like aluminum, which are called metals, which like to surround themselves by many atoms, not just one or two or four. Aluminum is such an example. Aluminum likes to be surrounded, each aluminum atom likes to be surrounded by 12 neighbors. This is really what makes aluminum happy. If he's surrounded by 12 friends, he's really happy. He likes, company, unlike hydrogen, which is quite lonely. Well, no, the most lonely elements, of course, are rare gases, right? They don't like to partner up with anyone else. But aluminum certainly is a good friend and likes to join company of other atoms, and in particular, aluminum likes to partner up with 12 friends. 12 friends is really the maximum you can think of, right? Because if you are, imagine you are a ball, and that's really the maximum number of balls you can be surrounded with. We'll come back to this in 2 or 3 lectures about packing of spheres. But, imagine yourself as a ball and imagine yourself as being somehow surrounded by as many balls as possible. You will immediately realize that 12 is the maximum number of balls that can surround you, of the same size, of course. If they are of different size, of course, there can be more or less. But if the balls have the same size, 12 is the maximum number you can accommodate around yourself. Okay, so aluminum forms this very nice closed, packed structures. Very regular, by the way. So we're starting to understand something new, or perhaps something you're already very familiar with, which is the fact that atoms like to arrange themselves in very ordered ways. This was really an exception. Actually, locally, there is a lot of order here, because each carbon is surrounded by 2 carbons. There are hydrogens here. If you take this piece of material, there is clearly a lot of order here. You could perhaps translate this forever. If this chain was a straight one, you could translate it orderly in a regular fashion, and that would really be a one-dimensional ordered system. Unfortunately, it is not, because this chain is very flexible, and therefore it likes to bend. Mechanically it will bend eventually, and it will form this complex material. So there is very little order in plastics, typically. You can grow crystals of polyethylene, but it's very rare, it's very difficult. If you take these chains and you try to pack them together, the first thing they do is just mess up and create a completely disordered system. Metals, on the contrary, like to form very ordered structure. They like to surround themselves by 12 neighbors, and each one of these neighbors will also like to be surrounded by 12 neighbors, and so this creates an ordered structure. Structure which we call a crystal. And we'll come back to this, of course, later on, about what we mean by crystal, all the mathematical properties, and so on and so forth. But for the time being, just, keep in mind the fact that when what I mean by an ordered system is the name I give it is a crystal. To an ordered system is a crystal. Now, will this crystal extend throughout my frame here, or not? No, right? Can I expect that if I take an atom here and I follow the sequence of atoms one next to the other one, will I be seeing this regular array of atoms all the way from the beginning to the end of the frame? No, right? So what happens in a real metal? Well, deformation is if I apply some stress, but here I'm not applying any stress. So what if I had my microscope and I was looking, instead of at this little piece, I was looking at something a little bit bigger than that? I would start seeing grains. Okay, I would start seeing domains where all the atoms are packed in a given way, and then suddenly there will be another crystal packed in a different direction. Well, I'm not very good at drawing crystals, but you can imagine, right? You have this regular system here, and you have another system here. So there are domains. Domains which locally are ordered, but then you jump from one domain to the other one, and the orientation is completely different. Random. unpredictable. So what really characterizes the properties of this material at the macroscopic scale is the size of these domains. These domains can be of any size. They are typically of the order of a few microns. If you take a microscope and try to understand the domain structure of this piece of frame of aluminum, you'll find it of the order of a micron. Okay, so the size of these domains will be of the order of a micron. Roughly, it can be 10, 100 microns, a fraction of a micron or something like that. We're talking about orders of magnitude. Of course, when I say this, I immediately imply that the distances between the atoms must be much smaller than the micron, right? I guess you're all familiar with the fact that distances between atoms are of the order of angstroms, right? Fraction of a nanometer. So when I talk about distances between atoms, I'm talking about an angstrom or a few angstroms. So we are 10 to the minus 10 meters. Here we are 10 to the minus 6. Okay, that means that we have hundreds, thousands, 10,000, 100,000 of atoms along a given direction before the grain terminates and another one starts. So they're quite macroscopic objects, these grains. In fact, turns out that the mechanical properties of metals are determined primarily by the size of the grains, more than by the way the atoms pack together. So this is also another example of what I was mentioning before. The underlying basic elements here was the same, but depending on how this was packing up at the mesoscale, that is intermediate between the atomic scale and the macroscopic scale, you had materials with completely different properties. Same here. The size of the grains will determine most of the mechanical properties at the macroscopic scale. Yes?
You say that chain is flexible, so it explains this structure. But what about this one? I see them as ordered. How do they form grains?
How do they form? So the question is, how do these grains form exactly, right? That's the question. Okay, that's a very good question. You have to consider how metals are typically created. How do you form these frames? If you work for an industry, you might be interested in knowing how you produce these frames. So these frames are typically produced out of a freezing process. You take the molten metal, you pour it into special objects with a given shape, with the shape of this frame, and then you cool the metal very slowly until it freezes. It becomes a solid. All right? Now, in the process of freezing, I'm now digressing a little bit from the ordinary course, of course, but that's a very good question anyway. In the process of freezing, temperature will, first will go down and will approach the freezing temperature. At that point, there will be places in the liquid in which crystals will start to nucleate. A bit here, somewhere there. There will be in my fluid, there will be places in which suddenly I will see the formation of small nuclei, seeds of the new crystal. Okay? And typically I have this process taking place in a large number of different places simultaneously when I bring my temperature below the freezing point. Okay? But now each nucleus will be growing independent of the other ones, and with a specific orientation which is just determined by the initial stages of the nucleation. At some point, when the temperature is brought even further down below the freezing point, these grains will grow and will touch, of course, at some point, and the liquid will essentially disappear, and the system will be composed of these grains. So the original orientation depends on the initial processes that gave rise to the first nucleus, the first seed, which was independent for this grain and for this grain. And finally, they have to touch, because when all the liquid becomes a solid, becomes a crystal, of course, you're left only with your crystals that were grown from the seeds. Okay? This is actually a very good point, because I'm now digressing into metallurgy. I'm even going even further away from solid-state physics into applied sciences, metallurgy. There is, of course, a lot of interest from a practical point of view in trying to find ways to change the size of the grains. There are applications for which you want your metal to be mechanically very soft. I'm not going to use material science wordings here, but I'll just use simple words like soft. You want material to be easy to work with. Well, in that case, you might prefer that your grains are small in size because you want to be able to rearrange your grains in a very easy way, okay? So the softness in some, I mean, quotation marks terms, depends on the size of these grains, and the smaller the grains, the easier it is for a system to readjust, essentially. You might easily see that it's more difficult to readjust the atoms once they are packed than at the boundaries here, where the packing is a bit looser. Okay? So it's easier to displace grains one with respect to the other one rather than to break a grain in the middle, of course, because the packing here is strong, and mechanically this object is much stronger than this interface here. Okay? So if you want your metal to have some properties to be easy to work with, you want your grains to be small. Okay? On the other hand, you want to perhaps build the blade of a turbine for an engine or for an airplane. And you want that material to be extremely strong, right? You want it to resist to extremely high temperatures. So you want it to have grain sizes as large as possible. Actually, ideally, you would like to have an entire blade being a single crystal, if possible, right? To be entirely made of a single piece of ordered material. In that way, you would completely remove all the boundaries, all the grains, and everything, and the material would be extremely strong. Well, that's exactly the way they build the blades in turbines. They try to remove as much as possible the existence of boundaries between grains. And how do they do it? Well, the way you do it is by cooling down your fluid extremely slowly. So slowly that as soon as the first seed, first nucleus appears, there are no other seeds anywhere else, and slowly this grain will grow, will grow, will grow, will grow, will grow until it covers the whole system. Okay, so you have a single grain, a material made of a single grain. We call them single crystals. Because they are crystals made of a single grain, a single ordered piece of crystal. They exist. And in fact, from a mechanical point of view, they're extremely strong. In fact, nature has given us several examples of single crystals, right? We want to produce materials very fast if you work for a metallurgical industry, but nature has produced minerals over timescales of millions, if not billions of years, right? In fact, the best examples of single crystals come from the Earth, from the minerals. Have you ever seen a piece of quartz with nice facets? Or any piece of mineral with nice... this is typically quartz, for example, which has hexagonal symmetry. So you'll see it forming crystals of this side. Whenever you have these nice facets, it typically means that the mineral consists of a single crystal, because this phase is typically the phase, the crystallographic phase, the crystallographic plane that identifies one of the different planes in your crystal. And there are beautiful examples in nature of single crystals centimeters wide, even, I guess, up to a meter big, of minerals. And they take this big single crystal shape because they grew up, they solidified, they crystallized out of geological timescales. There was perhaps a fluid inclusion made of a silicate melt that slowly on geological timescales cooled down. And so therefore, there was a time for the crystal to to crystallize with a single domain, a single grain. There are plenty of examples. I'm pretty sure you've seen them even in the stands in markets and other places, right? So minerals are a good example of single crystals, and the reason for that is that the minerals, some of them at least, form over geological timescales. So there is a long time for the melt to cool down and to form a completely oriented and ordered structure at the macroscopic scale. Okay? By the way, let me open another digression on a very nice story about this, on single crystals. There is another example, a huge example of something that might be close to a single crystal, and this is the core of the Earth. You know the Earth, right? The Earth is made of a mantle. So here is the mantle. Then there is a mantle is made of silicates, oxides, blah, 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 blah. Then there is a core, which is primarily made of iron. And this core is liquid here. So this is liquid iron. And the inner side of the core is solid. This is solid iron. Okay? I guess you're all familiar with this, right? This is something you learn in high school, I guess. If not in primary school nowadays. So let's focus on the core. So this is the core, right? So there is a fluid core and there is an inner solid core. By the way, we know this because of seismic waves. Seismic waves propagate when there is an earthquake here at the top. I'm talking about, Earth sciences here, but there is a lot of contamination between solid-state physics and Earth sciences, so this is one example of that. So anyway, there is an earthquake somewhere here at the surface of the Earth. The earthquake propagates the sound waves or seismic waves throughout the Earth. When the waves get to the boundary between the mantle and the liquid, this is a wave propagating between two different media. So there is reflection, there is refraction, there is a number of things. But in particular, in this particular interface, this is a boundary between a solid and a fluid. And if you have a little bit of familiarity with sound waves, you probably remember that while sound waves propagate in solids, both transversal waves and longitudinal waves, right? If you have a wave that propagates inside the material, if the material is solid, the density oscillation can be both transversal or longitudinal, right? If a wave propagates in this direction, like this, the density fluctuation can be either transversal, right, or longitudinal. These are completely different waves in principle from a symmetry point of view. In a solid. If you're in a fluid, the transversal oscillations don't exist because the fluid does not have any restoring force transversally. Okay? You can shear a fluid as much as you want. There is no restoring force that brings back a fluid if you shear it transversally. Okay? While there is, of course, a restoring force if you try to compress a fluid. So if you have longitudinal fluctuations of the density. Okay? So the bottom line is that longitudinal waves propagate in solids and in liquids. Transversal waves propagate only in solids. They don't propagate in fluids. In this seismic language, transversal waves are called shear waves. And these what are called, they should be called longitudinal waves, but they're actually called P waves. I'm using the seismic language now. So these are S waves, and these are P waves. They're called P because they're, for a historical reason, these are the ones that travel faster, okay, the longitudinal waves, So when you see the signal, you see them first. So and this is why they're called primary and secondary waves. Okay, so this S doesn't stand for shear, but it stands for secondary because you see them afterwards. While you see P waves, primary waves first, and these are longitudinal waves in seismology. But anyway, let me continue with this story. It's a very nice story. So you get this earthquake propagating seismic waves throughout the Earth. You get to this boundary. Shear waves get entirely reflected because they cannot propagate inside the fluid. P waves, they continue. And so if you take now a detector on the other side of the station, on the other side of the Earth, okay, you will only see P waves. You will not see the transverse waves, the shear waves. Okay? So this was the evidence that essentially, it's not that simple, but it was a little bit more complicated. But I'm making the story very simple now for you. That was the way in which seismologists could, say, conclude that there was a liquid region inside the Earth, because there were no transverse waves at, say, the antipodes, at the other side of the Earth when an earthquake was happening on the other side of the Earth, right? So the shear waves don't propagate, they get completely reflected. So here there are only longitudinal waves, and of course longitudinal waves then go throughout, and they're seen by the detector on the other side. Okay, so we know about the existence of a liquid core because of the way these seismic waves are reflected and refracted at the boundaries between the different layers that compose the Earth. But let me come back to my point, the original point, which was about this core here. Here we have a liquid iron, we have a solid core, and the Earth, was formed 4 or 5 billion years ago, right? And it was very hot at that time. In fact, the Earth differentiated over time. It was initially a completely molten piece of matter, and with time it cooled down and it differentiated, and therefore it formed the mantle, it formed the core, and the core, of course, is heavier. Iron is heavier, and so it precipitated towards the core. So what you see here is something that is reminiscent of the original Earth. You have a liquid core, which was the original state of iron, and you have a small solid that is growing very, very slowly out of the liquid. With time, this boundary is actually expanding because the Earth is cooling down, of course, on geophysical scale, not on year scale. We're talking about billions of years. It's slowly cooling down, and this solid is slowly growing. I forget now the rate. It's probably a millimeter per year or something like that. We're talking about very, very small numbers. But it is growing. So this piece of solid is slowly growing. It's actually probably the slowest ever growing material that we have seen in nature. So what would you argue about this piece of solid? By the way, this piece of solid is several thousand kilometers of diameter, right? It's not just centimeters like here. So what would you argue about that solid? It should be a crystal. It should be a single crystal, perhaps. So is it really a single crystal? Is it really a giant, kilometer-sized, giant piece of crystal where all the atoms are oriented in the same way across thousands of kilometers? That's a good question. We don't know the answer yet. But there are reasons to believe that this might be the case, or we might be close to that. It might be perhaps 2 or 3 grains only, not more than that. Still thousands of kilometers of size. And the way we know that is the following. If this is a single crystal, it will be oriented in some way, right? Suppose it is oriented in this way. Of course, it depends on the crystal, but suppose it is a crystal with some planes, and the planes are oriented in this way. Now, if you have a crystal, you might expect, and we'll come back to that later on, that the velocity at which sound waves propagate in the crystal are different if you propagate your sound in this direction or in this direction. The difference might be small, a few percent, up to 5–10%. It's certainly not going to be big. But you might expect some difference, right? Because the way you are perturbing the atoms in your sound wave is going to be different if you do it, if you propagate your sound in this way or in this way. So we estimate that the difference in sound wave, actually we don't know what the difference in sound wave propagation is for iron, solid iron at those conditions. But if we knew that, we would probably say that this is of the order of a few percent, the difference. Now, seismologists are now extremely good at telling us how fast waves propagate everywhere in the Earth. Of course, you might understand that it's very difficult to find out if you have a wave propagating in this direction and in this direction, whether there is a difference in propagation here and here, because this is hidden by all the propagation that takes place outside the core. So you really have to be able to detect very small changes in the timing at which two waves reach the detectors on the other side. But there is evidence in the last 10 years or so, and seismologists are really getting better and better at telling us differences in the speed of sound, particularly in the core. And there is evidence that there is a difference precisely of a few percent in the speed of propagation north, south, and east-west, or longitudinal across the Earth. Yes?
I guess with your theory, so
it's not my theory, by the way.
in this theory, I guess in many years
Yep.
in the future, so everything, I think there will be not the liquid.
Yeah. Correct.
There will be not the sea.
Magnetic field will disappear. Have you seen The Core, the movie? Well, you have to watch it. It's beautiful. I won't tell you the end, but it's really beautiful. Yes?
I know this thing. A massive object can drag the space-time curvature, right?
Can drag, sorry?
The space-time curvature, frame dragging.
Yes.
And then if this thing is growing with time, and then if we can know how much the space-time curvature is changing, then...
Oh, you're talking about space-time curvature.
A massive object can drag the space-time.
Okay, so your question is whether the growing of a massive object can change the space and time curvature and to an extent that we can detect it.
Yeah, so that we can tell more about this thing.
Okay, and whether we can tell more about this from these measurements.
I know they can drag the space-time curvature.
Okay, let me tell you the quick answer to this question. The answer is no, unfortunately, because the density of liquid iron is very close to the density of solid iron. So you wouldn't be able to tell, just based on density, whether you are solid or liquid. Okay? So you're not talking about a massive object growing out of a light object. You're talking about objects of the same density. Okay? It's just a piece of ice growing inside a glass of water. Actually, in that case, the density is even opposite, is even lower than in the case of water. Here, fortunately, solid iron is slightly more dense than liquid iron, slightly. Okay, so there's no change, unfortunately, in the freezing process. They're all massive materials, very heavy and massive materials.
Okay, I thought if we put something on the space-time and then if it's growing and then we see some curvature and then if we can detect this
Sure.
thing, then...
Okay, so your question is whether we can detect it based on the fact that you have a massive object growing with time. But unfortunately, the densities are the same. So as far as the mass is concerned, mass is always the same, essentially. Okay, good. So we might have a giant example, a giant single crystal growing inside the Earth. We don't know it yet. We don't know it yet. Actually, one of the challenges is the seismologist parts. The detecting differences in the propagation of sound waves is, of course, a challenge from a seismological point of view. But the other challenge is from solid-state physics, because if I measure a 2% difference in the propagation of sound waves, how do I know whether this 2% corresponds to the difference between two propagations in my crystal? Could it be something else? I need to know, if I want to prove that this is a single crystal, that the difference in which sound waves propagate this direction and this direction is precisely 2%. If that was, say, 10%, for example, and what you measure is only 2%, Well, then you might argue that there are some grains and there is some preferred orientation. So the grains preferentially orient in some direction. But, I mean, it's only 2% on average, because if we were just taking a single crystal, it would be, say, 10%. But we need to know this. We need to have this information in order to be able to say that there is a single crystal. So this is where solid-state physics comes into play. If we were able to calculate or predict or measure the sound wave velocities of iron, unfortunately, at these conditions. Here we are at about 5,000 Kelvin and 330 gigapascals. So we are about 3.3 10 to the 6 atmospheres. A million atmospheres. No experiment yet has ever been able to get to those pressures. We are close. I mean, there are experiments currently being done in France. They are getting to about 1 million atmospheres. So it's only a factor of 3 off. And I guess in the next few years they might be able to get there experimentally and trying to measure the sound waves. Of course, then you must be able to grow a small single crystal in your lab and then do the experiment with sound waves in different directions. It's a challenge, but it's not impossible, of course. All right. End of the digression. Yes?
Okay, what I've got from you is that when you're talking about a single crystal, then the propagation in maybe sound, when you go in this direction,
Yes.
should have a big difference compared to this.
Few percent is enough. So your question is, this implies that, I mean, for this to be true, there must be a difference of a few percent, or there must be a difference between the propagation, the sound velocity propagating in two different directions in the crystal.
What about for a material like now?
Oh, you mean made of grains?
Yes, made of grains.
No way. So if the material is made of grains, then if you look at the macroscopic propagation of sound, it will propagate with the same speed, because on average, sound propagating this way, we see on average all possible directions, right? So it will go fast here, it will go slow here, fast here. On average, it will go some average velocity, which is the average of all possible velocities in the crystal. So this is exactly the principle that would explain the presence of a single crystal. Because we know that there are differences in the propagation of sound velocities in the Earth core, north-south and east-west, the only possible explanation is that it is not made of small grains, because otherwise the speed would have been the same, would be the same. Okay? So there must be some orientation. Of course, the question is whether it is due to a giant single crystal, or perhaps to 2 or 3 single crystals, grains, or perhaps, that would be even more subtle, due to many, many, many small grains like these ones, but preferentially oriented in a given way. Okay, so still random, but with small preference for, say, an orientation of the grains in this direction, north-south. Then, of course, the question is, what causes this orientation? Why should a crystal orient like this, or like this, or like this? I mean, this is... now, there are theories for that. I mean, geoscientists are being able to come... I mean, whatever is the phenomenology you know, I mean, you can come out with an explanation for that. So there are theories that try to explain why you should have the crystal aligned in a given or in another direction, based on the, essentially, to the asymmetry generated by the rotation of the Earth. Yes? Yeah.
The general state of the iron, I think, involves some energy.
Sorry, the general state of the iron is?
Yeah, involves some energy.
Evolves?
Energy.
Oh, yes. You're talking about the latent heat, or what?
No, from liquid to solid.
Yes.
Needs some energy.
Yes, correct. You're perfectly right.
Where does that energy come from?
No. It's actually the opposite. You are crystallizing a system, right? So you're taking a fluid and you are forming a solid. Okay. So you are releasing energy.
Okay, well,
Where is this energy going? Yes. Oh, it's one of the. In fact, if you measure the heat, you can measure the amount of heat that comes from the ground. In fact, there are quite precise measurements of this amount of heat. Those of you who will take geosciences as a future studies, you will know that this can be measured quite accurate. The amount of heat that the Earth produces. So you might ask yourself, where does this heat come from? Well, portion of this heat comes from the fact that the Earth is slowly cooling down. So there is some primordial heat that was there because the Earth was very hot at the beginning. Okay, so it's something that is slowly cooling down. But this is not the only contribution. There are two other contributions. One is the radioactive contribution. Actually, that's the dominant one. So radioactivity inside the Earth is generating heat, and this heat propagates towards the surface, and then it's what we measure. But there is a third contribution, and this is the latent heat produced by the freezing of the iron core. This is, there is a debate about what is the percentage of that, but this can be a sizable contribution to the overall, what they call heat budget of the Earth. How much heat comes out of the Earth. 10%, 20% of that heat was generated by the freezing of the iron core.
So there's no contribution of the sun.
Now we're talking about heat going away from the Earth. That's going down, right? So it's that's influx. You're talking about heat generated in the Earth, and of course at depths. You don't want to measure it, say here. You want to measure it, say, few meters below the ground, right? Because you want to avoid the fact that you have the heat, generated by the sun. The fact that you're heating the soil just because of the sun. You want to measure the real contribution coming from the Earth. More questions about this? Yes?
Does it mean that by changing how you cool your liquid, instead of having a polycrystalline, you can have amorphous material?
Yes, correct. So the question is whether if I cool my crystal with a different rate, I can generate even an amorphous system, a disordered system. The answer is yes. If I cool it very fast, now you've learned the lesson, right? If you cool it very slowly, you get the perfect crystal. If you cool it very fast, you can get something which is disordered. Unfortunately, for metals, this is very difficult to reach. So it's very difficult to get a disordered metal. Metals, find their partners very quickly. Okay, so it's very, with the fastest rate that you can consider, you rarely see something which is completely disordered. But there are other systems for which this property is not, true, and which form a disordered system. Take glass, for example, right? Take a melt made of silicates, you cool it down. Getting a crystal out of a silicate melt is difficult, on the other hand, right? So you have the opposite problem. You need to cool it down with time scales of the order of several years if you want to form, say, if you take from Sio2, I'll come back to that in a second, by the way. Let me now take another system. Let me take Sio2, silica. This is a very common material. By the way, this was the next step because silicates are what make concrete, for example, right? Stones, everything that looks like, marble. Well, marble is carbonate primarily, but they're very similar in properties. Okay, so let's focus on the simplest one, which is Sio2. I'll come back to the question in a second. Let me explain before what does this system look like if I look at it at the microscopic level. What would I see if I took a piece of silica glass, for example, okay, window glass. I take window glass, which is primarily silica. I take my microscope. What would I see? Well, I would see this kind of structure. So I would see that each silicon is surrounded by an oxygen, and so on and so forth, of course. So I would see that each silicon is surrounded by 4 oxygens, and each oxygen acts as a bridge between 2 silicon atoms. Generally speaking, of course. Then there are defects, there are impurities, there are a number of other things. But the basic building blocks of my structure are these entities. In fact, mineral scientists like to call this tetrahedra because you have silicon in the center, 4 oxygens going outside in tetrahedral direction. So this really looks like a tetrahedron. So they like to visualize these objects by using tetrahedra, linked together through the corners. You see, you have a tetrahedron here. And you have a tetrahedron there. So they are tetrahedral linked by the corners. Now, if you take this system and you cool it down very slowly, geological timescales, what do you get? What is the name of this crystal? Does anybody know? What is this? What is the name of a crystal made of SiO2? Quartz. Come on, it's quartz. One of the most beautiful crystals that we... Quartz. So if you crystallize it very slowly, geological timescales, you get quartz. If you crystallize it, if you cool it down, if you take a melt, you put it in a furnace, you melt it, it's a fluid. It's glowing actually because it's very hot. And then you cool it down on time scales of minutes, hours, seconds, minutes, hours. Yes?
When you cool it down, you add plus hydrogen or...
No, there's no hydrogen here. Why do you want hydrogen?
Cool it down by which energy?
Oh, well, you just, I mean, if you want to do it slowly, you just take your melt and you leave it there and just wait in some, of course, container that can contain it. You don't need to put water, anything. I mean, you put water if you want to make it very fast. But even if you take a fluid silicate, you leave it there in a container, in a metal container or something, and you just wait until the heat slowly dissipates, time scale of minutes, hours, even days. No way you get to quartz. The dynamics is so slow that there is no time for the system to grow crystals, ordered systems. The atoms just arrange themselves. I mean, just look for the first neighbors and then they stop. I mean, there's nothing they can do. They just freeze out. So you invariably end up, so this is the crystal, which you will never get. And what you get actually is a glass, which is a disordered version of quartz, essentially. So window glass is just a disordered version of quartz. In fact, it shares the same properties, more or less, right? It's transparent like quartz. But it's made of the same atoms. It's simply obtained in a different way. Fast cooling, fast. For this particular system, even the slowest one that we can achieve, say, with our human scales, will lead you to a glass, to a completely disordered system, to a system in which if you jump from one to the other one, there is no regularity at all. Okay, so we're at the other extreme of the, okay, so this answers your question. So this is a case in which whatever is the quenching rate, you get something which is completely disordered. You will never get a crystal unless you wait for thousands of years. And you do the cooling very, very slowly, geological times. In order to get a single crystal of quartz, you really have to wait long time. No way you can do it in an experiment. Okay? So we're on the other extreme. In fact, if you take any material which is made of silicates, again, concrete, marble, whatever, I mean stones, you rarely see crystals there. They're all essentially disordered. Well, stones is different because stones, they are formed geologically, okay? So because they're formed geologically, there was time to form small crystals. In fact, if you take a stone and you look at it microscopically, you will see crystals, you will see grains like you see in aluminum. There are nice pictures in textbooks of grains with different colors if you do this polarization spectroscopy of crystals. Okay. Yes. Now, let me discuss now another important concept in solid-state physics, which is the concept of crystal. Again, we are going to discuss it in much more detail in the next lectures, but what I would like to do now is to just clarify why we like crystals and we don't like glasses in solid-state physics. We like crystals because they are ordered. Okay? So we like to work with crystals because as soon as we learn how a crystal behaves locally here, we know for sure that what happens here is exactly the same as what happens far away, because if it is a crystal, it is ordered. The way if I sit here or I sit somewhere else and I look around me, I will see exactly the same, right? So the purpose of the reason why we like crystals is that they simplify the job for us considerably, because it is enough for us to understand what takes place locally here to understand what takes place everywhere in the crystal. Mathematically speaking, this is slightly more complicated because what we're going to take advantage of is not only the local properties, but is also the translational property of the system. Is the fact that if I apply translational symmetry, and you've already seen this, I guess, in your quantum mechanics classes, you're going to learn something important about the mathematical structure of your properties, of the functions you're going to work with. We'll come back to that later on, so you don't need to think too much of these concepts. The only thing I would like you to keep in mind is that in solid-state physics, we like to work with crystals. They make our life extremely easier than if we had to work with glasses. Glasses would be a mess, because if I sit here, I would see an environment. If I sit here, I see another environment. What am I going to study? How am I going to study a system of 10 to the 23rd particles if each one of them has a different environment? Much easier to work with crystals. Of course, when I do this, when I make this kind of reasoning, I always have to keep in mind that real materials are not made of crystals. And this is precisely why I made all this digression over crystals, amorphous, and grains, and all this. Because we're going to spend a lot of time on the properties of crystals. Actually, we're going to spend 90% of our time on the properties of crystals. But where are crystals in nature? They're, nowhere macroscopically. We always need to keep in mind that whatever material we take, with a few exceptions, unfortunately, like glass, like a few others, like plastics, for example, the properties of my system will be primarily determined by the properties of my crystal. And on top of that, if I want to be more precise, I will add the consequence that having grains has, how these grains perturb the properties that I determine based on the single crystal. Okay? So the way we will approach the problem in solid-state physics is by assuming, in most cases, actually in the 99% of the cases, that the system is a crystal. Okay? Always to keep in mind that this is not really the case. In fact, there are no, even for macroscopic crystals, there is an end at some point, right? Ideal crystals where there is translation periodicity forever, at infinity, don't exist in nature. You either get to the end of the grain, or you get to the end, even for single crystals, even if they are the size of centimeters, at some point you'll get to the end, you get to a surface. Okay? So there are no infinite crystals in nature, but we need to start our analysis starting from a crystal, and then we need to understand how much this analysis is going to be affected by the fact that the real material is not a crystal. Now, an interesting consideration to make at this point is that a large number of properties, with a few exceptions, which we already discussed, of materials can be understood at the atomistic microscopic level. Take, and we'll come back to this, optical properties, for example. Okay, whether a system is transparent or not, or is opaque, or is conductive, for example. Now, these properties are independent of whether the system is made of grains or not. Right? A piece of aluminum made of grains or made of single crystal will conduct electricity the same way. There's no difference. A piece of glass will be transparent to light precisely like quartz, like the crystalline counterpart. Right? They don't differ. They're both transparent, perfectly transparent. Why is this so? Because these are all properties that depend on the local order of the atoms. The fact that quartz and glass is transparent depends on the way the atoms are arranged here, locally. And this is the same in the crystal and in the glass. Conductivity, the metallicity of the problem, is determined by the way the atoms and the electrons pack together at small length scales of the order of the atomic distance. The resistivity of a piece of aluminum, there will be, of course, small differences, but not something you can clearly think has a major impact. So there are a number of properties that actually most of them that don't really depend on the fact that we are dealing with grains, or we're dealing with disordered system, or we're dealing with the crystal. Okay? So that's why, not only because we like to work with crystals that we do it, but also because a number of properties don't really depend on whether we're dealing with a crystal or whether we deal with the amorphous disordered counterpart, as long as we talk about the same elements, the same system. Okay? So let me now... yes?
Are there some properties of materials that depend on the crystal?
On this, well, we discussed them at the beginning. Remember mechanical properties. A plastic bag is different than this one. This is not something I would be able to predict based on the crystalline state of polyethylene, which is a big piece of crystal. I would never be able to tell you that the plastic bag is softer than this cover. Okay, so there are properties like mechanical properties for which I won't be able to tell you anything if I was studying the ideal crystal, for example. In fact, most, say, mechanical properties are affected by the size of the grains, what people call the mesoscale. So the scale which is neither the microscopic one nor the big macroscopic one, the visible one. So mechanical properties are an example that sometimes is used to mention the effects of the size of the grains. And so the differences between a crystalline and an amorphous system. Yeah. Okay. Okay, so now that we have learned that a number of properties are determined by the local arrangement of the atoms, let me step back a little bit and look at what are the ingredients that we will need to consider in solid-state physics. Okay, so we've started from the top, and we've looked at materials around us. We've tried to understand how we can somehow percolate down this complexity that we see around and try to identify some elements that we would like to retain. We have seen that the concept of crystal is extremely useful, although with all the discussion we've made, we also realize that we need to always make sure that the properties that we're interested in are not affected by the size of the grains, by the macroscopic structure of the material. And now we're going further down, and we're going to try to understand at least what kind of ingredients we will need in the next lectures in order to understand the properties of materials at the microscopic scale, at the atomistic scale. Okay? So we go down to the basic building block, the brick that is going to allow us to construct the whole picture of solid-state physics. And this is the atom. Okay? The atom is really our building block. Whatever we do, we will have to start our understanding based on the properties of the atom. And of course, the challenge of solid-state physics is to understand how you can go from the isolated atom to an understanding of the properties of matter when you take several atoms together. Okay? So what we're going to, I mean, the basic, area of study of solid-state physics is really the understanding of what are the consequences of taking several atoms together and bringing them together. How do the properties of atoms change, for example, when you bring them together to form a solid? So in doing that, I'm somehow going to give for granted that all the rest has been solved and understood. We're not going to study atomic physics again, but I'm going to assume that some concepts in atomic physics are familiar to you. If they're not, I will have to ask you to look at your textbooks, preferred textbooks in atomic physics, and try to refresh those concepts. There is a limit, of course. We cannot go deeper and deeper and deeper. Otherwise, we will never start our process of understanding from the atoms to the solids. So we have to stop at some point, and we will stop at the atomic level. So I'm going to assume that you are more or less familiar with the structure of an atom. Not to great detail. In fact, I'm going to refresh those concepts in a second, the ones that are more important, at least in solid-state physics. But before I do that, I need to make sure we all agree on the terminology and what is the physics that we are not interested in, or at least that we give for granted because someone else has studied it, someone else has understood it, and it's giving us information that we will use to construct our theory of the solid state from the atoms. So I'm now going to digress on the other side of the length scale, right? I'm been digressing on the large length scale limit, macroscopic limit. Let me now digress a little bit of what lies outside solid-state physics, but on the other side, on the further scale of length which goes further down below the atomic scale. I guess you're all familiar with this, but I just want to make sure that we use the same language and we understand each other when we talk about these things. So let me really go back to basics, right? We have, in nature, we have, I'm a theorist, right? I'm a theoretical physicist, so I like to classify and to go back to basics. And so I guess we all know that in nature we have 4 fundamental forces, gravitational, electrostatic, weak, strong, and so on and so forth, right? So where are we going to place these basic concepts into what we're going to study in the future, solid-state physics? Well, there is certainly a few forces that are totally relevant to us. Can you name some of the forces among these fundamental forces, the ones that are irrelevant to us, solid-state physicists? Gravitation. She's saying gravitation. Gravitation is certainly quite irrelevant to us, right? Because the way atoms pack together doesn't really, is not really affected by gravitation. Of course, when you go to the macroscopic scale, the fact that the body falls is, of course, an effect of gravitation, but we're not really interested in this sort of big macroscopic phenomena. We're interested in, again, packing atoms. So gravitation is not going to be of interest to us. Good. What else?
Other things, okay. Strong force is irrelevant in the order of...
Strong forces, very good point. Strong forces are irrelevant to us. Not that we are not interested in the fact that they exist, because if they didn't exist, the nuclei wouldn't exist. And if the nuclei didn't exist, we wouldn't have the atoms, right? But we sort of forget about strong forces. Someone else, our colleagues in nuclear physics, are studying strong forces, and we take for granted from them that nuclei exist. Okay? For us, the nucleus is a good starting point. The nucleus is a good starting point because it's the next step beyond the atoms if we go further down, right? If an atom is made of nuclei, a nucleus, and electrons, so we need to know that the nucleus exists. So for us, the nucleus is going to be an object, a point-like object. I'm drawing a sphere now, but what I mean in my mind is a point-like object with a given charge, obviously, right? So typically, this charge is denoted by the atomic number, Z. And so we know that the charge of a nucleus is Z times, where Z is the atomic number, times the charge of the electron. This is what we care in solid-state physics, or in atomic physics at least. The details of what's inside here are totally irrelevant to us. Well, there's probably a second quantity that we might be interested in, and that's the mass, the weight of this nucleus. Because the mass of this nucleus is going to determine, to a large extent, the mass of the atom, right? The electrons are much lighter, so the mass of an atom, the weight, the density of matter, is going to be determined by the mass of the nucleus, primarily, right? So we might also wish to know the mass of this object. And as you probably know, this mass is determined both by the number of protons, right, and by the number of neutrons that you have in your nucleus. But again, the fact that there are neutrons and protons and all this is certainly not of interest to us. We're not going to discuss neutrons and protons and all that. We're just going to retain from nuclear physics the fact that the nucleus has this charge and a given mass, which is the sum of the masses of protons and neutrons plus some energy and blah, blah, blah. But all these are details for us, are not important. Not that they are, of course, not important in physics. They're not important for us in solid-state physics. Which means that LHC is totally irrelevant for us. What's going to happen at LHC is, for us, totally irrelevant. Not that it's not worth doing those experiments. I'm now doing a little bit of advertising again. But if we could get a little bit of those money for solid-state physics, it would probably be a bit better. Anyways, LHC is totally relevant for us, right? LHC is going to probe matter at a scale which is much, much smaller than this one. Strong forces, even weak forces, are irrelevant for us, right? Weak forces are those that, again, keep to some extent the nuclei together, strong and weak forces. And so, nothing that could be important for the rest of the course, essentially. Yes?
But sometimes this weak force or interaction is responsible for beta decay, right?
Yep. Okay, so what he's arguing is that weak forces are responsible for beta decay and?
Okay, to bind the nuclei together.
Right.
So, it's not really...
No, I'm not arguing that it's not important for physics. I'm arguing that I need to focus on something, right? I need to study my course. I need to pass my exam, right? I can forget about beta decay if I'm studying solid-state physics. If I want to leave some room for all what we're going to study, which is a lot, I need to put this beta decay on the side. Of course, if asked by someone else, I need to be ready to answer what is beta decay and weak forces.
Sometimes those things that we thought they are something simple, they are...
Of course. And in addition, I should say something more. There are, in fact, some interesting properties that are interesting in solid-state physics, which actually depend on the structure of the nucleus. A number of experiments, think of radioactivity, for example, or think of Mössbauer spectroscopy, which is an interesting spectroscopy that is currently used to probe the state, the electronic state, even the electronic state of a solid. They're all based on a knowledge of the structure of the nucleus. I'm arguing, of course, that this is probably only 1% of the whole field of, and so the contamination with fundamental physics, nuclear physics, exists. It must exist, of course, because the two are related, right? They cannot be completely disconnected. But for the purpose of, say, introducing solid-state physics in 20 lectures, I need to somehow put the boundary somewhere, because otherwise we're going to be flooded with interdisciplinarity and with, already this digression on geophysics was probably a bit too much, a bit too bold. I spent probably too much time on that, so I need to focus a little bit. Okay, so strong force is irrelevant, weak force is irrelevant, gravitation essentially irrelevant. What's left? Electromagnetism. Okay, So electromagnetism is going to be our main force, and the only one, essentially. So I'm listing here the basic ingredients. Electromagnetism, the nucleus, with some properties that are reminiscent of the nuclear structure, right? Mass and the charge. What else? Oh, what other ingredient are we missing here? Obviously. The next one, the nucleus, the electron, right? So the electron. The electron, we know the mass, about 2,000 times smaller than the nuclei. Actually, to be precise, 1/836 proton masses. I guess you're all familiar with this, right? I don't need to really refresh those concepts. I mean, I hope you're already familiar with those concepts. So we have the electron with its own mass, the charge, which is E. There are Z electrons in an atom with atomic number Z. Electromagnetism is needed. What else? What other theories do we need to study solid-state physics? Quantum mechanics, right? We need quantum mechanics. Do we need classical mechanics? We also need classical mechanics, I guess. Although, of course, classical mechanics is an extreme case of quantum mechanics. It's much better to work with classical mechanics whenever possible, right? Instead of trying to derive everything from a quantum mechanical point of view. Do we need anything else? Do we need quantum field theory or anything like that? Well, there are examples where we might need quantum field theory, but again, they belong to this, probably not 1%, but 5% tails that we need to discard and cut. Otherwise, we'll never be able to conclude a course like that. So we essentially need quantum mechanics, classical mechanics, electromagnetism, nuclei, electrons, and we are done. In principle, not in 20 lectures, but in 100 lectures, I might be able to derive solid-state physics as a whole, starting from these 3, 4, 5 elements. Okay? No way we can do that in 20 lectures. So I need to make a few additional approximations, and I will also need to somehow limit the areas that we are going to cover in this course. Yes?
The quantum mechanics, is it like the classical one or the relativistic one?
Oh, very good point. Sorry, I forgot about it. Yes, relativity. That's another important theory. Do we need it? Sorry. Relativity. Do we need it?
If we consider, for instance, the sun as one object, then...
If we consider, sorry, what?
The sun, our sun, like...
Sun?
Yeah. I mean...
Oh.
Okay, if we consider things at high temperature...
Okay, very good, very good. So the question is, well, relativity implies that, well, a number of things. It implies that objects must be moving close to the speed of light. I've never seen a piece of crystal moving at the speed of light, but you never know, of course. There are temperatures, of course. If you go deep inside the sun, for example, there might be phenomena that... well, of course, the photon is... unfortunately, there's nothing we can do with the photon, right? We cannot slow down the photons yet. So photons must move at the speed of light, at least in vacuum. And we're going to deal a lot with photons, at least towards the end of our course. So yes, relativity in the sense that photons are included, yes. But I would say this is part of electromagnetism. Even if we didn't know what a photon is and we knew Maxwell's equations, we would be able to solve our problems anyway. So allow me to perhaps remove even relativity from our... Again, there is this 5% of phenomena that do require relativity. And there are actually quite important ones. I mean, take magnetism, for example. Although, of course, magnetism, but again, if I take Maxwell's equations for granted, I'm also taking relativity for granted, right? I hope you're all familiar with this, because Maxwell's equations imply relativity in some sense, right? So the speed of light is there. So magnetism is, in principle, a consequence of relativity, but it's trivially included in Maxwell's equations. So I don't really need to treat them relativistically. There are, however, a phenomena like, for example, spin-orbit coupling. We're not going to discuss spin-orbit coupling in any detail, but even at the atomic level, atomic physics, if you study spin-orbit coupling, the constant that is in front of the coupling, spin-orbit coupling is the term in the Hamiltonian that depends on L dot S, angular momentum scalar spin, in the Hamiltonian, well, in any Hamiltonian, I mean, for an electron at least. And the term in front of this object, don't ask me the exact details of that, but it contains C here, 1 over C. So clearly, this is a term that without relativity would disappear. Okay, if C was infinity, spin-orbit coupling would be absent from our picture. Again, spin-orbit coupling is important in solid-state physics, but it's only, say, covering this few percentages that we are not going to discuss in this lecture. So allow me to say that relativity is not going to be crucial for solid-state physics, of course, unless it is already included in Maxwell's equations, which is... I guess it's time to stop now. Yes, another question? Oh, the books. Yes, a very good point. I'm not going to use any books. Particularly, I mean, since these lectures are recorded, the book is the recordings. So I want you to know what we discussed in class, and I would like you to also take a look at textbooks as an independent source of information. But the exam will be based entirely on what we've discussed in class. So in principle, if you're lazy, you can just come to class and take your notes, and the notes are your textbook.
So he is not support. You will not give.
I will not give any lecture notes, although there will be 2 postdocs in charge of collecting information about this course. But as far as the exam is concerned, there will be only classes, your notes, and what we've discussed in class. I need to warn you, however, that I will occasionally, not so occasionally, actually quite frequently, give you some tests, okay? I will tell you in advance, of course, but my idea would be once every week at least to have a quick test at the beginning of the lecture, something like 5 multiple choice questions about what we have done in the previous lectures, so that you come to the lectures prepared, okay? I don't want you to come to the lectures and forget what we've done before. So I would like you to come and be prepared. So I would like to give you, I guess we will do it next time on Monday. We will do, say, 10, 15 minutes. There will be a multiple choice, 5, 6 questions based on what we've discussed in the first 3 lectures this week. Okay? And there will be, and this will be part of the final evaluation. And then there will be a final exam at the end, of course. Yes, sorry, yes. So the book I like most, and I like it a lot, it's Solid-State Physics by Ashcroft and Mermin. There are plenty of copies in the library, by the way. There is a special shelf in the library reserved for diploma students. I don't know if you noticed. I think it's at the entrance to the right. And there are plenty of copies of Solid-State Physics by Ashcroft and Mermin. I'm not going to cover the full book, of course. I'm just going to cover a few aspects out of this book. But large part of what I'm going to discuss is contained in Ashcroft and Mermin. And I particularly advise you to consider this book because I really like the way the concepts are introduced. Nothing is left unexplained in this book. If you read this book, you will find that all the words are carefully chosen, all the statements are carefully chosen, they are all logically following from the previous ones. So I like this textbook a lot. It's not complete, unfortunately. It doesn't include optical properties, for example. It includes very little of optical properties. There is a choice of topics. It's not covering the full spectrum of solid-state physics, but I particularly like it because it's very enjoyable to read, and it's the way, the logics of the logical flow is extremely strict and rigorous. So I like particularly this book. The other very popular textbook is Introduction to Solid-State Physics by Keaton. Charles Keaton. Mind you, there are several textbooks by Keaton, actually at least two of them, on solid-state physics. You better choose the introductory one. There's one which is called Introduction to Solid-State Physics by Charles Keaton. And this is probably the most popular textbook in solid-state physics. I mean, I don't dislike it, but I personally prefer this one in terms of this somehow, Keaton sometimes he gives some concepts for granted. So you somehow out of the blue, you're introduced to new concepts without even knowing what they mean. And so from the pedagogical point of view, I like the more Ashcroft and Mermin. Then, I mean, you probably have thousands of other books. And my personal suggestion is that don't limit yourself to these ones, nor to the ones that you find immediately on the shelf. Take a look at them and find the one that you like most. The most efficient way to learn is to compare information that you get from different sources. So the reason why I don't like to, actually I did it already, but I don't like to force you to use a textbook is because I think the learning process is faster if you listen to my lectures and then you go back to a textbook and perhaps find something different. And then you come back to me and say, why did you tell it that and the book tells me something else? That's actually very positive for your critical mind. So I would really advise you to take a look at different textbooks and choose the one you like most. Perhaps, I mean, you come from different backgrounds, so it's also important that you find the textbook that better matches your previous knowledge about the topic. But as far as I'm concerned, what we do in class is in principle enough, but all of it, okay? All of what we do in class is part of the final syllabus and curriculum that you would like you to know. Any more questions?
Is there a course outline?
Sorry?
Course outline for the course.
Good point. I'll give it to you. I'll give it to you soon. Yes, I need to. Yes, I need to think about it, particularly for the last part. But I'll give you an outline in the next days, the next lectures. Yes. Are we done? Yes.
Will we have a tutorial lectures?
A good point. I wasn't considering so because I typically do tutorials whenever we need to do problem solving. I didn't think really that we should spend too much time on problem solving here. This is an introductory course after all, so I'm not really going to ask you to solve real problems in this field. I'd like you to learn the general concepts, so I'm not really sure whether there is need for tutorials. However, if you feel the need, I'll be more than happy to arrange some tutorials. Even private, I mean, even for a few of you, if you feel that you have some gaps in your background. Okay? Any more questions? Okay. See you on Wednesday then.